Hi everyone. I decided to make this video to explain a little bit of how can we write some conditional constraints in integer programming model using just a simple example problem that I made. And I'm going to try to explain the problem in a way that it's more intuitive, not just mathematically. I would like to guide you through my thought process and how I would approach this type of problem if I was going to solve it for myself. So the problem is that I have a 3D printer and I want to use it to make some plant vases made of PLA. And I have 3 designs to choose from: the moon, the rocket, and the star. Each type of vase will require some amount of resource of material to be made, and I have a limited amount of resource available for me. There is also a setup cost that will happens whenever I prepare the printer to make a specific type of vase. So every time I change, I will have to pay $200. And because of the costs, I decided that once I set the machine to make and to print one type of vase, I will print all the vase that I need of that type. The price on the market also have a different price for each type. And what I want with this is to maximize my profit, what I want with this model. There are also some characteristics that are related to my marketing strategy, and they are all conditional statements that we will have to translate into an IP problem. So first we have to define the decision variables. That's the first step. And the decision variables are kind of in our face. It's kind of obvious because I have already stated that we have 3 different designs to choose from. So we have, if we have some choices that have to be translated into the model. And another thing that we can use as clues for which variable is going to be our decision variables are the parameters that are directly related to our possible variables and also directly related to our goal, that is to maximize profit. So if I want to maximize profit, I will probably have some revenues and costs, and those revenues and costs will have to be associated with some decision variable normally. So this one is, of course, is the types: the moon, the rocket, and the stars are going to be one of the 3 of the decision variables, but we have another variable also that is the one related to the setup cost that is necessary to prepare the printer. So this cost here will have to go into the objective function. So we will need some variable to associate with it. The last thing for us to consider in this paragraph are the resource availability constraint. So first, the decision variables. The first decision variables, the set of decision variables, is the one that we discussed. It's the type of vases: moon, rocket, and star. But the decision variable xy is going to be the number of vases that we want to print of each of those types. We are going to assume that we are not selling half of us, so the xi are going to be positive and integer. But we have the setup cost, and we have another set of variables that we need to write down. So if I decide to manufacture the moon vase, I will have the setup cost to set the printer to the moon vase style. And if I decide not to manufacture the moon vase, I will not have that associated cost. So Because it's just have or not have costs, I can use a binary variable to define this type of cost in my objective function. And that's what I'm going to do. I'm going to define yi as a binary variable that is 1 when type I vase is manufacturer, or whenever xy is greater or equal than 1, and 0 when type I vase is not manufacturing, which means that xy is less than 1. Those two variables, I now can make my and write down my objective function. And as I stated, I want to maximize my profit. And so maximizing my profits is the sum of all the revenues minus the sum of all the setup costs, because it's the only cost that I have. Translating this into an equation, it's going to be the equation that it's shown over here. What I have to worry about now is the constraint that is stated in this first paragraph. And that's this constraint of resource availability. And it's pretty straightforward. I'm not going into that, but that would be the equation. Now, another problem that we have is with that term of the objective function. Because, of course, we define here, there is no equation, but there is no equation here that shows us that this will happen. So if we have only this constraint and this object function, what will happen is that the y I variables are always going to be 0, because there's no constraint here. There are no constraint here forcing this to be anything but 0. So that's what we need to do now. We need to come up with constraints that will force these yi variables to be 1 when they need to be 1. So how to do it? What that definition means mathematically. It means that if xy is greater or equal than 1, which means if I'm producing some base of y type, then yi is going to be 1. And that's what I need. Let's see all the possibilities of that happening, of xy and yi. So the possibilities are to be xy to be 0, or xy to be greater or equal than 1. And for yi, it's just 1 or 0. So in these first situations, this statement is going to be true. But in the last one, this statement here, it's not true, it's false. So how can I find a relationship here, an inequality equation that will represent this relationship here, these statements here being true, and this last one to be false. To help us figure out how to do it, the best way is to focus on the false statement. So what relationship between these two variables is going to be false and under this situation? So this here, it's always going to be greater than 0, right? So if I put unless or equal to, I will have a false statement. So that will work for me. But let's see if the same relationship would work for all the rest. If we test from the one from the top, that doesn't work anymore, because I need this statement to be true, but this statement is false. So what can I do when this happens? If we decide to multiply this number here for a really, really great number, a number so big that x1 will never be that big. What would happen is the statement would become true. And that's why we use the big M method. The big M is just a big number, a big enough number to make the situation work for us. If we multiply yi to this big M, I will have all the statements true using this relationship. Because this one here will still be false, this one here now is true, and the others remains true. That can be translated to the set of equations xy is less or equal to big M multiplied by yi for all the y's. And this will be written down in our model. So now we added for each type a different constraint that will ensure that anytime I have any production of one type, I will have a setup cost accounted for here in the objective function. Now we have to worry about the second paragraph. There are the characteristics of my marketing strategy. We are going to focus on the first two because they are both related to the idea that I will have a set of moon and stars that I want to sell together. So this is our problem. And this is the constraint that I want to design right now. First is the star vase is not sold without the moon vase, but the moon can be sold independently. That can be translated to if ys is greater or equal than 1, then ym should be equal to 1. And the second one is the set of star and moon vases have at most 3 stars for each moon, which means that I need a new moon vase every time that I make more than 3 stars vases, which can be translated to in mathematical form to xs divided by 3 is less or equal to xm. That's the same thing as xs is less and equal than 3 times xm. So now I have these two sets of two statements that I need to translate into a constraint in my IP problem. So let's focus on the first one. The first one is ys equals 1, then ym equals to 1. So in this case, for this statement to be true, these are the conditions, and this statement is only going to be false under this last condition over here. And for this statement, for this statement to be false, it's easy to know that I can only add this relationship. If I add this relationship, then this will be false, and the rest are going to be true. So that's exactly what I want. So a very easy way to model this is just making the relationship of ys has to be less or equal to ym. But when you compare these two equations and we remember the relationship between xs and yx and ym and xm, we easily realize that this one is way more limiting than this one. So this one is inside in this one. So if this is more limited, this one will be redundant. So we don't need to write this down in our model because we are already writing this down in our model. So that's what we are going to do. We are going to add. So we are going to add this constraint here in our IP model in construction. The third conditional statement that we're going to work is, if I make the stars, I will not make the rockets, which can be translated to ys equals, if yx is equals to 1, then yr is equal to 0, which is the equivalent to the logical statement ys, if ys, then not yr, that is equivalent to not is or not ir. That is an or statement. It will be ys equals to 0 or yr equals to 0, which can be easily represented by this, because the summation of these two variables are always going to be less than 1, but in the time that this statement 0 is false. So that's exactly what we want. And then we can model this as ys plus yr has to be less or equal to 1. And that's going to be our constraint. So the last one is, I need to print at least 3 moons or 2 rockets. This can be represented by xn greater or equal than 3 or xr greater or equal than 2. In this example, I decided to make a little different for you to see that you can model this and try to come up with the logic behind it in different ways. The idea is the only way that's going to be false, the statement is going to be false, is when both of them are not true. But when only one of them are true, I can work this out. Okay, so to make that possible, I'm going to use an auxiliary variable that will allow me to turn on one of the inequalities or the other. And how do I do this? First, I have this auxiliary variable that is going to be the w, and it's a binary variable and has no definition. It's just a tool for us to be able to model this conditional constraint. And what I will do is that it will be connected to each of those equations, and it will be connected by w multiplied by one set of equations, and 1 minus w multiplied by the other equation. What will happen is that when w is equal to 1, so this equation is going to be valid, but this term here is going to 0, so this whole equation is going to 0, and so xr, it's not going to be limited by anything, only xm. So it's like saying that just this equation here is working, just this inequality. But if, on the other hand, w is equal to 0, then this thing here has no value. It's going to be 0 equals to 0, but this thing here will start working. So we are turning on this one and turning off this one. Then just xr is going to be more or equal, but xm will have no limitations to it. So that's the set of equations that we have to write down for us to be able to conclude our IP model. Of course, we have to add this auxiliary variable here in the decision variables, because it's not like a decision variable, but it's going to vary depending on the decisions that we need to make this objective function to maximize our profit. So that's it. That's the final IP model. And if you have any doubts, please contact me. Bye-bye.